Welcome to a genuinely new way of seeing. You've spent years in math dealing with fixed shapes and static equations, but the real world is constantly changing. Calculus is the toolkit built specifically for that change. Instead of asking what is the area of this rectangle, we ask how fast is this car moving right now, at this exact instant. The secret is a process of infinite zooming. Imagine looking at a curved graph so closely that a tiny segment appears perfectly straight. That local straightness lets us apply simple algebra to complex curves, giving us shockingly precise answers about motion, growth, and accumulation. This module builds that intuition from the ground up, which is essential for every physics and advanced math problem you'll face in your IIT-JEE preparation. You already think in a calculus-like way more often than you realize. When you're walking to meet a friend and constantly update your arrival time based on your current pace and the distance left, you're intuitively working with a rate of change. When your phone estimates battery life, it's not just using a simple average, it's analyzing your current usage rate to project a future state, which is a foundational calculus concept. This same thinking scales into powerful careers. Engineers use it to calculate the exact stress on a beam not just on average, but at every single point, preventing catastrophic failure. Medical CT scanners don't just take a picture, they use calculus to reconstruct a 3D image from thousands of tiny X-ray absorption measurements. Even in economics, the decision to produce one more unit of a product hinges on a marginal cost and revenue, a direct application of the derivative you'll learn here. So, the most important takeaway is to reframe calculus in your mind right now. It's not just a harder version of algebra, it's a conceptual upgrade that lets you handle a dynamic universe with precision. That mental image of zooming in on a curve until it becomes a straight line is the key that will unlock derivatives and integrals for you. Every formula we build will trace back to that simple, powerful idea. As we move forward in this course, this foundation will be what makes complex physics problems and advanced math feel like a coherent story, not a collection of tricks. Your homework, starting today, is to actively notice rates of change in your daily life, the speed of a shadow moving, the rate at which a cup of tea cools. That awareness is the first step to thinking like a mathematician. Welcome back. In our last session, we saw calculus as a new lens for seeing reality, a way to understand change and motion. Today, we give that lens its two sharpest focal points. Calculus, at its heart, answers two big, practical questions. The first is, how fast is something changing at this exact instant? Think of glancing at a car's speedometer, it tells you your instantaneous rate of change, your speed right now. The second question is, given how fast you've been going at every moment, how far have you actually traveled? That's the odometer's job, it accumulates all those instantaneous speeds over time to give you total distance. These aren't separate ideas, they're two sides of the same coin, and seeing their connection is what makes calculus so powerful. We'll use the car analogy throughout to make this concrete and visual. Let's dive into the first big question with our car. Imagine you're accelerating onto a highway. Your speedometer needle is moving, it doesn't show your average speed over the last minute, it shows your speed at this precise moment. In calculus, we call this instantaneous rate of change the derivative. If we plot your speed over time on a graph, the derivative at any point is simply the steepness, or slope, of that curve at that instant. A steeper slope means faster acceleration. Now, flip the question. Your speedometer tells you your speed at every second, but how do you know how far you've gone? You can't just multiply speed by time because your speed keeps changing. The integral solves this by mentally slicing your journey into infinitely many, infinitesimally thin time slices, calculating the tiny distance covered in each slice using the speed at that moment, and then adding all those tiny distances together. On a speed versus time graph, the total distance is exactly the area under the curve. So, what should you carry forward from this? First, whenever you hear a derivative, think of zooming in on a single moment to see how something is changing right then, like the speedometer's needle at a precise second. Second, when you hear integral, think of patiently adding up a continuous stream of tiny changes to find a total effect, like the odometer tallying distance from a varying speed. These are your two fundamental tools. They aren't just abstract concepts, they're inverse operations that give you two different but complementary views of any changing system. In our course, as we tackle the IIT-JEE problems, constantly ask yourself, am I being asked for an instantaneous rate or an accumulated quantity? Drawing the graph, even a rough sketch of speed and distance side by side, will often reveal the answer. You now hold the two master keys to calculus. In our next session, we'll start learning the precise language of limits, which allows us to define these ideas with absolute rigor. In your earlier math work, you spent a lot of time solving equations like x squared equals 4, where the answer is a static number. Calculus asks a fundamentally different question, not what is x, but how does one quantity behave as another changes continuously? To make this leap, we need to stop seeing functions as just formulas that spit out a single result. Instead, picture a function as a dynamic machine. You feed in a value, it processes it, and produces an output. Now imagine turning a dial on the input side, smoothly varying the input, and watching the output respond in real time. This mental animation is the heart of calculus. It lets you see a function as a flowing relationship, not a frozen snapshot. When you later encounter limits, you won't just be plugging in numbers, you'll be watching a process unfold, getting closer and closer to a moment of change. Let's build on the idea of the function machine. Take a simple function like f(x) equals x squared. In pre-calculus, you might ask, what is f(3), and get the static answer 9. But in calculus, we ask, what happens to the output as x slides from 2.9 to 3.1? You're not just interested in the destination, you're interested in the journey. As you slowly increase the input, the output doesn't just jump, it traces a smooth curve, speeding up because the function is steepening. This continuous response is what a limit captures, the value the output is heading toward as the input approaches a point. Once you internalize this flowing behavior, a derivative becomes a natural next step. It's simply a measure of how sensitive the output is to a tiny nudge in the input at any instant. And an integral? That's just adding up all those tiny output changes over an interval, like tracking the total distance traveled when you know your speed at every moment. To truly prepare for the calculus ahead in this course, make a habit of animating every function you encounter. When you see f(x) equals sin x, don't just memorize its graph, imagine a point moving along the x-axis and the output oscillating smoothly in response. This mental movie is what turns the abstract definition of a limit into something tangible. You're watching the output settle toward a specific value as the input hones in. From there, the derivative becomes the natural question, how fast is the output changing right now? And the integral becomes, what is the total accumulated output over this stretch? Start with functions you already know well, like x squared, root x, or 1x. Slowly vary the input and describe aloud what the output is doing, speeding up, slowing down, approaching a boundary. Many students hit a wall when they first see a limit expression where the denominator seems to vanish. The phrase "it's approaching zero" can feel like we are about to break the number one rule of math, never divide by zero. But here is the secret that changes everything. In calculus, we are not actually landing on that forbidden point. We are taking a journey towards it, watching a pattern unfold, and asking what value the pattern is confidently heading towards. Think of it like walking towards a wall. You can get arbitrarily close, your nose almost touching it, without ever crashing. That final destination is not part of the walk, but the direction of your walk is perfectly clear. This shift in perspective, from static calculation to dynamic process, is exactly what our earlier discussion on dynamic functions prepared us for. We are going to make this journey visual and completely demystify the fear of the infinitely small. Let's ground this with a powerful visual from geometry, which directly answers the first big question calculus asks about instantaneous change. Imagine a square drawn snugly around a circle. It is a rough fit, with big gaps. Now, double the sides to an octagon. The fit is better, the gaps are smaller. Keep going, a 16-sided polygon, then a 64-sided one. As the number of sides increases, the polygon's shape gets smoother and its area gets closer and closer to the circle's area. Here is the crucial point: at every single step, we have a real, finite polygon with a measurable gap. We never, ever create a polygon with infinite sides. That phrase is a poetic summary, not a literal object. The limit is not the last step of an endless process, the limit is the circle itself, which the process is approaching. So, take a deep breath and let go of the idea that a limit is a sneaky way to divide by zero. It is a completely new operation, a dynamic lens for watching a function's behavior on a journey. When we write that something approaches zero, we are saying we can make the gap smaller than any challenge you can name, a process that is perfectly rigorous without ever touching the endpoint. The polygon sequence shows that the abstract idea of infinitely small is really about a concrete, never-ending process of refinement. This visual intuition is your anchor. Whenever you see a limit later in this course, recall the polygon smoothly hugging the circle tighter and tighter. You are not looking for a forbidden value at the destination, you are reading the clear, confident direction of the journey. This is the foundational mindset that turns the fear of infinity into the power of calculus. In our journey through calculus, we have already seen how limits allow us to tame infinity and how functions describe dynamic change. Now we arrive at the single most important visual secret in all of calculus. Take any smooth, unbroken curve and pick a point on it. From far away, the curve bends and twists. But if you imagine a magical microscope that zooms in closer and closer onto that single point, something astonishing happens. The curve straightens out. That tiny, almost invisible straight segment is the heart of the derivative, the tangent line, and the entire idea of linear approximation. This is not just a neat trick, it is the geometric foundation that turns the abstract limit definition into a picture you can see and trust. Once you truly internalize this zooming in effect, the derivative stops being a formula to memorize and becomes a natural, visual fact about smooth change. Let us walk through what the microscope actually reveals. Imagine a parabola, which clearly curves when you look at the whole graph. Place your mental microscope right at the point where x equals 1. At low magnification, you see a pronounced bend. Increase the zoom. The curve begins to flatten. Zoom in 100 times closer, then 1,000 times. Eventually, the graph on your screen looks indistinguishable from a perfectly straight line. That line is not some separate object we draw later, it is what the curve itself becomes at that scale. The slope of that tiny straight segment is precisely the derivative at that point. This is why the derivative gives the instantaneous rate of change. It is the slope of the curve when you look so closely that the curve forgets it was ever curved. This also explains why linear approximation works. If you stay extremely close to the point of tangency, walking along the tangent line keeps you almost exactly on the original curve. So what should you carry forward from this visual revelation? First, whenever you encounter a derivative or a tangent line in a problem, do not just push symbols around. Pause and picture the microscope. See the curve straightening out at that single point. This mental image will protect you from confusing the tangent line with a secant line that cuts across the curve. The tangent touches at one point because, when you zoom in, the curve and the line become one and the same thing right there. Second, this idea gives you a powerful sanity check. If a function is smooth, you know a derivative must exist because you can imagine zooming in and finding that straight segment. If a function has a sharp point, like an absolute value graph at the origin, you know instantly that no single straight line can match the curve from both sides, no matter how much you magnify. Finally, remember that this local straightness is the permission slip for all of differential calculus. Welcome to a core idea that makes calculus so powerful, the integral mindset. You've already seen how limits let us tame infinity and how zooming in makes curves look straight. Now we're going to use those ideas to build up a whole from tiny, manageable pieces. Imagine you want the area of a circle but don't have a formula. You could slice it into thin concentric rings, unroll each into a flat strip, and stack them into a shape you do know, a triangle. Or think about a car's changing speed. If you break the trip into tiny time intervals where speed is nearly constant, each interval gives a small rectangle of distance. Add them all up, and you have the total distance traveled. This slicing and adding process is the heart of integration, and it turns hard, curvy problems into simple, straight-line approximations that become exact in the limit. We'll build this intuition step by step, always tying back to the dynamic functions and limits you've already mastered. Let's walk through the slicing process carefully. First, you need a strategy. For a circle, concentric rings work beautifully because each ring's circumference is easy to measure. For distance from speed, vertical time slices make speed nearly constant in each interval. Next, you approximate each slice as something simple, a rectangle for the unrolled ring, or a rectangle for the speed time slice. The area of one ring becomes roughly circumference times thickness, and one distance slice becomes speed times time. Now sum all those little bits. At first, this sum is only approximate because the slices have curved edges or changing speeds. But here's where your limit knowledge kicks in. As you make the slices thinner and more numerous, the error in each slice shrinks, and the sum gets closer to the true total. In the limit, the sum becomes the exact area or distance. So what should you carry forward? Integration is fundamentally about accumulation, gathering up infinitely many tiny contributions to get a whole. The beautiful visual of a circle's area turning into a triangle when you unroll its rings is not just a trick, it's a genuine insight into how curved shapes relate to straight ones. Similarly, whenever you see a speed-time graph, remember that the distance traveled is exactly the area trapped beneath the curve, built from those skinny rectangles. The key habit is to mentally slice before you reach for a formula. Ask yourself, what am I adding up? How would I approximate one slice? As you make the slices thinner, the approximation improves, and the limit gives you the exact answer. This mindset will serve you throughout the course, from simple areas to volumes, work, and beyond. Keep visualizing, keep slicing, and trust the limit process you've already learned. It's your bridge from the approximate to the exact. Welcome back. So far, we've explored calculus as a new lens for seeing change, and we've tackled the two big questions it answers: how fast something is changing at an instant, and how to add up infinitely many tiny pieces. Now we're going to reveal something almost magical. Those two questions, finding slopes of curves and areas under them, are not separate topics. They are inverse operations, like addition and subtraction. To see this, imagine a car trip. You have a distance graph showing your position over time, and a speed graph showing your velocity. The height of the speed graph at any moment tells you exactly how steep the distance graph is at that same moment. And if you look at the area accumulating under the speed graph between two times, that area precisely equals how much your distance changed. This deep link is the heart of calculus, and today we'll visualize it with a moving tangent line and a filling area, side by side. Let's build this connection step by step. Picture a distance-time graph that curves upward as the car accelerates. At any instant, we can draw a tangent line touching the curve. The slope of that line is the car's speed right then. Now, if we plot that speed value as a point on a separate graph below, its height directly matches that slope. As the car speeds up, the distance graph gets steeper, and the speed graph rises. That's the first link. The speed graph is a picture of the slopes of the distance graph. Now flip your thinking. Look at the speed graph alone. If we start shading the region under it from the start time to the current moment, the total shaded area tells us how far the car has traveled. Why? Because we're adding up all the tiny distance bits, each one is a speed multiplied by a sliver of time. So the area under the speed curve reconstructs the change in distance. So what should you carry forward from this? First, whenever you see a graph, you can now think of it in two complementary ways. Its height at a point can represent the slope of another, hidden graph. And the area under it can represent the total change in that other graph. This isn't just a neat trick, it's the operating system of calculus. The derivative, which we've been using to find instantaneous rates, and the integral, which we'll use to sum slices, are inverse tools. Just as squaring and square roots undo each other, differentiation and integration undo each other. When you're solving problems, this unity means you can often translate a hard area question into an easier slope question, or vice versa. Keep the car animation in mind. The moving tangent line and the filling area are not separate phenomena. They are the same story, told from two perspectives. This insight will make everything from physics to engineering feel more connected and intuitive as we move forward. In the earlier parts of this lesson, you saw how calculus gives you a new lens on reality. Limits let you zoom in until curves look straight, and thinking in slices reveals how slopes and areas are inverse operations. But none of that power comes from just memorizing derivative rules. When you face the IIT-JEE, problems are designed to break pure recall. What works instead is building mental models, rich, visual, physical intuitions where each symbol has a concrete meaning. In this section, we will contrast the trap of rote formula memorization with the lasting strategy of genuine understanding, and show you exactly how to make that shift using the concepts you have already begun to explore. Let us make this practical. First, whenever you see a function, sketch it. That simple act forces you to see the slope as a moving tangent line, not just a formula. Second, translate symbols into physical language. If you see dV/dr, say out loud, "This is how fast volume changes when I stretch the radius." That ties the derivative back to the slicing and zooming you already learned. Third, verbal explanation is a superpower. Try teaching the idea of a limit to your empty chair, and you will quickly find gaps in your own understanding. Fourth, use graphing tools like Desmos to slide parameters and watch how the slope and area under the curve respond in real time, making the hidden connection between slopes and areas a lived experience. Finally, always anchor new rules back to the foundational ideas. The product rule is not a chant, it is what happens when you zoom in on a product of two changing quantities. As you move forward in this Calculus Foundations module, commit to replacing passive formula sheets with active mental animations. When you see a rate of change problem, do not just hunt for the derivative rule, replay the mental movie of zooming in until the curve looks straight. This visual and verbal practice is what creates the resilience you need for the IIT-JEE, where problems twist familiar patterns in unfamiliar ways. Using technology to explore graphs is not a shortcut, it is a laboratory for your intuition, letting you test your mental models instantly. Remember, a memorized formula evaporates under stress, but a deeply understood concept, built from limits and slices, becomes part of how you see the world. That is the true mastery this course aims to give you. As we move forward in this Calculus Masterclass, you might notice the concepts feeling more abstract. That sense of challenge is actually a positive sign. When your brain grapples with limits or the idea of instantaneous change, it's building new neural pathways. This is genuine learning, not a sign that you're falling behind. In this lesson, we'll acknowledge that difficulty directly and then reframe it. We'll look ahead to how the mental models you're forming now, zooming in until a curve looks straight, and thinking in slices, become powerful tools in physics, data science, biology, and economics. Remember, you've already covered the core insights, limits, dynamic functions, and the hidden connection between slopes and areas. Now we'll use those to fuel your motivation for the road ahead. First, let's talk about the struggle itself. When you're working through a limit that doesn't immediately make sense, or trying to visualize how secant lines become a tangent, that mental friction is where deep understanding takes root. In the IIT-JEE context, this grit is as valuable as any formula. Second, consider where this leads. In physics, the zooming in idea lets you derive instantaneous velocity and acceleration from position functions, exactly what you'll need for kinematics. In data science, the concept of a derivative helps optimization algorithms find the best fit line. The adding up slices idea directly underpins probability distributions and expected values. Even in biology, population growth models use differential equations, and in economics, marginal cost and revenue are pure calculus. These aren't distant applications, they're built on the very mental models you're forming now. The course will keep returning to these two simple, visual anchors, so when abstraction hits, ground yourself in the picture. So here's what I want you to carry forward. The entire calculus you'll encounter in this masterclass rests on two beautifully simple, visual ideas. The first is zooming in until a curve looks straight, which gives you the derivative. The second is adding up tiny slices to build a whole, which gives you the integral. Every new technique, every complex application, is just a variation on these themes. When the material feels abstract, mentally step back and ask, is this about a rate of change at an instant, or about accumulating a total from pieces? That question will guide you. The confusion you feel now isn't a wall, it's the fog that clears as you climb higher. In upcoming modules, we'll repeatedly return to these anchors with more powerful tools, and what seems fuzzy today will snap into focus. Trust the process, and trust that your brain is doing exactly what it needs to do.